Hey guys, welcome back to my channel Informatics. In this episode, we will be learning about our nearest star to the Earth, the Sun. That's right, there are billions of stars in our galaxy, the Milky Way. The nearest one and the one that is giving us light and warmth is our star, the Sun. The Sun is the biggest, the hottest, the most massive object in the solar system. Its incandescent surface, which means its brightful surface, bathes its family of planets in light, and its immense gravitational force choreographs their orbits. The Sun is a typical star, little different from billions of others in our galaxy, the Milky Way. Now, the Sun, its immense size, compared to any of its planets, the Sun is immense. The Earth would fit inside the Sun over 1 million times. Even the biggest planet, Jupiter, is a thousandth of the Sun's volume. But that does not mean that the Sun is the biggest star. VY Canis Majoris, known as a hypergiant star, it can fill about 3 billion suns. Wow! Our star will not be there around forever. Now, halfway through its life, the age of the Sun is 4.6 billion years now. Now, after 5 million years, it will turn into a surging, swelling out towards the planets. Mercury and Venus, the first two planets near to the Sun, they will be vaporized. The Earth may experience a similar fate, but even if our planet is not engulfed, it will become a sweltering furnace under the glory of a closer sun. Eventually, the Sun will shake itself apart, leaving behind a ghostly cloud known as a planetary nebula. Alright, so this is how much important the Sun is to us. It gives us the adequate amount of light and warmth. Now we'll take a look at the Sun's, how it produces energy. So it may seem like an unchanging yellow ball in the sky, but the Sun is incredibly dynamic. The Sun has no solid surface. It is made up of gas, mostly hydrogen. The intense heat and pressure inside the Sun splits the gas atoms into electrified state of matter known as plasma. The density and temperature inside the Sun rise steadily towards the core, where the pressure is 100 billion times more than the atmospheric pressure on the Earth's surface. 100 billion times more than the atmospheric pressure on the Earth's surface. Now, here it's an unique environment. Nuclear fusion occurs. Here, hydrogen nuclei are fused together to form helium nuclei, and a fraction of their mass, is lost as energy, and which reaches slowly towards the outer layers of the Sun and escapes into the darkness of space, eventually reaching the Earth as light and warmth. Now we'll take a look at the Sun's structure. Alright guys, so this is the Sun's structure. Now we'll start from the core of the Sun. Now, making up the inner fifth of the Sun, the core is the where nuclear fusion creates 99% of the Sun's energy. Now, the center of the core, where hydrogen has been fused, is mostly helium. The temperature in the core is 15 million degrees Celsius. Next, we'll go to the radiative zone. Alright, just about the core. Now, light energy works its way slowly up through the radiative zone, colliding with atomic nuclei and being re-radiated billions of times. The radiative zone is so densely packed with matter that energy from the core can take as long as 100,000 years to reach the surface. That is very, very slow. Alright? Now, the radiative zone accounts for 70% of the Sun's radius, and temperature range from 1.5 to 15 million degrees Celsius. Alright, now we'll go to the convective zone. In the convective zone, pockets of hot gas expand and rise towards the solar surface, that is the Sun's surface. The process known as convection carries the energy upwards much faster than in the radiative zone. In the radiative zone, it takes us 100,000 years to reach from the core to the surface. All right, but here it's much faster. In the convective zone, it's much faster than in the radiative zone. Temperatures here vary from 5,500 to 1.5 million degrees Celsius. Alright, so between these radiative zone and convective zone, there's a tachocline, okay, tachocline layer. Now, in the tachocline layer, the tachocline is a transition region between the radiative and the convective zones. It plays an important role in the generation of the sun's dynamic magnetic field, okay. So this tachocline, it has an important role in the generation of the sun's this magnetic field. All right, then we have the photosphere. The photosphere is that a region only 100 kilometers thick. All right, then it is the apparent surface of the sun. All right, it's the surface of the sun. Now this is where energy reaches the top of the convective zone and escapes into the darkness of space. Now the temperature here is 5,500 degrees Celsius. Now this photosphere is just the surface of the sun. All right, the temperature of surface of the sun is 5,500 degrees Celsius. Same like that, photosphere it's 5,500 degrees Celsius. Now there you can see a prominence, like a loop of fire coming out there. A prominence. All right. Now it is loops of gas emanating from the photosphere. Now, it stretches hundreds and thousands of kilometers into space, these prominences. You might have noticed in some of the pictures of the sun, all right? And then we have the sunspot. It is cooler regions of the photosphere, that is the surface. They are visible as dark patches known as sunspots. All right. So this is the um, important suns, the structure of the sun. All right. So by this we finish the topic um, about the sun. There's a lot of information more to recover. All right. So when I get more information, I'll do it in another video. All right. I'll share it with you. All right. So in the next episode, we'll be learning about the solar eclipse, and we'll start about the rocky planets, those Mercury, Venus, and all. Or you'll be knowing that in the next video. All right. So I'll see you guys in the next episode. Thanks for watching. Bye.